Exercise 2.26. For the truss shown, express the position vector RAD from point A to point D in terms of components. Use your result to determine the distance from point A to point D. Alright, so there are actually three ways in which we can solve this exercise. We're going to do them as a set, and then we're going to explain the concepts that we require or that we needed for us to solve the exercise. So the first way is by using a summatory of vectors. Now, the vector that we require is the vector AD. This vector. Now, this vector is the solution between this vector adding this vector. That means that the vector RAD is going to be equal to the summatory between the vectors RAC and RCD. Right? So RAD is equal, right here, RAD is equal to RAC plus RCD. Now, RAC is equal to minus 1.2 meters along the I direction minus 0.7 meters along the J direction. The vector RCD is equal to minus 0.6 meters along the J direction plus 0.4 meters along the J direction. We're going to explain why later, right? At this moment, we only care about the solution. Now, the vector RAD is going to be equal to minus 1.8 minus 0.3 in meters. Hence, the magnitude is going to be this one. Square root of 1.8 square plus squared plus 0.3 square. The magnitude of the vector RAD is equal to 1.8248 meters. And right here we have the first way for us to find the results. The second way is by using the same methodology but with these two vectors. The vector RAV and the vector RBD. Now, the vector RAV is going to be equal to minus 1.2 plus 0.6 plus 0.4 minus 0.7. 0.7, and right here we have our component for the J direction, and right here we have that the vector RBD is going to be equal to minus 0.6 on the I direction minus 0.6 along the j direction. This part is equal to minus 1.2 along the I direction. Right here we have a whole unit, 0.6 plus 0.4 minus 0.7 is equal to plus 0.3 on the j direction. Now, adding these two, I'll have the answer that we need. Our AD is going to be equal to minus 1.8 on the I direction minus 0.3 along the j direction. Right here we have the same answer, and therefore we have the same magnitude. Now, the third option for us to solve this exercise is by using the components of the points A and D, more specifically the coordinates. So the coordinates of the point A are actually 1.8, 0.7, x, y. And the coordinates for the point D are 0, 0.4. That means that the vector RAD is going to be equal to the coordinates of the final point, which is D because of the direction, minus the coordinates of the initial point. That means that I should subtract 0, 1.8 and 0.4, 0.7. Minus 1.8 minus, along the I direction, minus 0.3 along the j direction. And right here we have our third option for us to solve this exercise. Remember that you have to take into account the magnitude. So the distance from point A to point D is the magnitude of the vector, and the magnitude is the same one for these three vectors. Now, the concepts that we needed for us to solve this exercise. The first one, for when you want to create a summatory of vectors, graphically speaking, all you have to do is to create a resultant shape. For example, if I want the result of this vector is going to be generated between this vector and this vector adding each other. Why is that? Because as you can see, the head of this vector is touching the tail of this one, and the result is going to be the other way around. The tail of the resultant vector has to be touching the tail of one of the corner vectors. Why is that? Because if, for example, I have something like this, not two vectors but three, then the result is going to be this one. Remember, tail with tail, head with head for the result. This required hat has to be met for when we want to solve this exercise, taking into account a summatory of vectors. Now, taking into account the position of every vector is pretty important. Why is that? Because you have to take into account your zero. For example, the vector RAC is generated between the summatory of these two components. As you can see, both of them are pointing towards the opposite direction of y and x. For example, this component is pointing towards the opposite direction for y positive. That means that this should be negative, as well as this. Because of this, right here we have x positive, and this vector is pointing towards the other direction, so this should be negative as well. Another example, the vector RCD. The vector RCD. The vector RCD is generated between the components because of these two components, this one and this one. As you can see, the component in y is pointing towards the same direction for the positive numbers of y. That is why I is positive right here and negative right here because of this component. Now that this is clear, you can solve this exercise by adding these two. Alright, so minus 1.2 plus minus 0.6 is actually remain this subtraction. That means that I have minus 1.8. Minus 0.7 plus 0.4 is equal to minus 0.3. Right? The same explanation works for this other part. But the difficulty was taking into account the components of this vector, so we're going to check it. RAB. Now, RAB is generated between this component and this component. As you can see, the component that regards the x direction is pretty easy because we already have it, 1.2. But the component that we have right here is not that easy to see. Why is that? Because all I have to do is to subtract this whole part, this little part, for me to find this other part. Alright? You can check once again the video if you didn't understand it. But I should subtract this whole part, this part, for me to be able to find the component that we need. That is why I did this. And as you can see, this is positive. That is why I did this. And as you can see, the component regarding the x direction is negative. This is why I did this. Alright? And the summatory between these two is actually made as well as this one. It's actually the same. I already explained this other part. Of course, I think that this method is easier. And that would be all, guys. This is how you can solve this exercise.